Hello students, so welcome back to the class. So we will be continuing our chapter Structure of Atom. Disclaimer, the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that part of the content may have been generated using generative AI, which is experimental. In this lecture, we would be seeing the de Broglie relationship and the Heisenberg uncertainty principle. So what are the subtopics? So this is basically a start towards the quantum mechanical model, which includes the dual behavior of matter and its related problems. Then the uncertainty principle given by the Heisenberg. So if we see the previous discussion, we have seen that the existing Bohr model was incomplete and it was unable to explain most of the part. Okay, but still it is a great advancement in the atomic model. Now, there were some reasons because of which the Bohr model failed. So we will look at the two reasons, or I would say the two aspects which Bohr didn't consider and due to which his model failed. So these are the two aspects that he didn't cover. So first was the dual behavior of matter. So in his model, he was not concerned about the dual behavior. He was only concerned about the particle nature of the electron. Second thing was the uncertainty principle. We will study about both of them. What are these principles and how did they lead to the new quantum mechanical model? So first of all, we will study about the dual behavior of matter. De Broglie was the one who gave an equation for the dual behavior of matter. So he said that if you have a radiation, okay, if you have an electromagnetic radiation or any other radiation, or if you have a matter, they both have the property of wave and as well as particle. Not only the matter has the dual nature, but the radiations also have the dual nature. So this is important to note. This was given in the 1924 by the French physicist de Broglie. So for example, if you consider a photon, so photon is what? Photon is a, you can say, a constituent of light. Now it will have wavelength, okay, and it will have momentum also. So momentum is related to particles because they have the mass and the velocity, whereas the wavelength is related to the wave nature. Similarly, electron also has momentum as well as the wavelength. Now, how do we relate these two different and distinct properties? So we are talking about two types of properties. One is a wave type and one is a particle type. So wave type is wavelength and particle type is momentum. So the equation that was given to relate both of this was lambda is equals to h by p. Okay, or we can write it as lambda is equals to h by mv. So p is the linear momentum whose formula is m into v. So this equation is very, very important for you. So what are m and v? Of course, m is the mass of the particle and v is the velocity of the particle, whereas p is the momentum, or you can specifically call it as linear momentum, because there is one more term which is the angular momentum, but we will only consider the linear momentum here. Got it? Now, the part that is to be focused is that every particle that you see around which is moving, okay, or every particle that you see, whether it is a table or a chair, it will have a wave like nature. Okay, so you will say that why don't we see cars moving like a wave? Okay, instead it is moving straight. So basically the de Broglie equation is not that much significant for the macroscopic particle, means bigger particles. What is the reason behind it? Let us try to understand it with the help of an example. Okay, so as I have mentioned earlier, so every object, irrespective of its size, whether it is bigger, that is macroscopic, or smaller, that is microscopic, it will have a wave-like character. But the point is that the ordinary object, which are bigger in size, they have a very short wavelength. Okay, and as a result of this short wavelength and its large size, two things. So wavelength is short and its size is large. Okay, now due to this, its wave nature cannot be detected. Got it? Is it clear? Now next, so the wavelengths, whereas we are associated with the electrons and the other substance like the subatomic particle, so they are large enough to be detected, or they are significant for microscopic particles. So two things are there. First is, due to the very small wavelength, the wave nature of the bigger particle is not observable, whereas for the smaller particle, where the wavelength is large enough according to that particle, okay, so the particle is very small and the wavelength is also comparable to that size. Due to that, it is detected experimentally. Now we will see an example to understand that. Suppose we have a ball. So ball has a mass of 0.1 kg and it has a velocity of 10 meter per second. Then what will be its wavelength? So I will request you all to write the answer in the chat section. So what will be the wavelength? Simple formula. Apply that formula and get your answer. So h was the Planck's constant. You must know the value. It is 6.26 into 10 to the power minus 34. Now we will use the de Broglie equation, which is lambda is equals to h by mv. So lambda is the wavelength. We are interested in calculating the wavelength. Just put the values here. So h value is 6.26 into 10 to the power minus 34 joule second. Unit is important. Then 0.1 kg n is the mass and 10 meter per second is the speed. It's given here in the question. Okay. If you calculate this, you will get the value as 6.26 into 10 to the power minus 34 meter. Now you can see very clearly that why this wave nature is not that much significant for the ball. So compared to the size of ball, which is having a mass of 0.1 kg, this wavelength is very, very small. So it must be moving like this. Okay. But since its size is large, it would appear that it is moving in a straight line. Okay. Is this point clear? So this is very important to note. Now let us take the example of microscopic particle. For that, we can take this question. So it is given that the mass of an electron is 9.1 into 10 to the power minus 31 kg. And its kinetic energy is also given. It is 3.0 into 10 to the power minus 25 joule. We have to calculate its wavelength. How you will calculate it? So to calculate wavelength, we need two things. First is mass. Second is the velocity. So mass is given here. We can get the velocity from the kinetic energy. So which formula we would use to calculate the velocity if we know the kinetic energy? Any guesses? So if you are given the kinetic energy, how will calculate the velocity? Yes, we will use the formula half mv square. So very simple. Just put the values that you have. So this is the formula. Kinetic energy will be equals to half mv square. Just rearrange it to get it. V is equals to 2 into Ke by m raised to the power half. So as square goes on to the next side, it becomes half as the power. So kinetic energy is given here. Very good. Mass is given. So we got the velocity. So this will be the velocity, 812 meter per second. Now what are we interested in? We are interested in the wavelength. We'll use this formula again because now we have all the values that we require. So if you put all the values, you will get this thing. So mass is 9.1 into 10 to the power minus 31 kg. Velocity is 812 meter per second. Calculated here. Joule second is the Planck's constant, 6.626 into 10 to the power minus 34. Now you will get 8967 into 10 to the power minus 10. You can convert this thing into nanometer. It's very simple to convert this thing. Okay, I hope it is clear. Now there is a question for you. So this question is very interesting and a good one. So what is given in the question? You are given the wavelength of the photon. It is 3.6 angstrom. How you will calculate the mass? So from the same formula, lambda is equals to h by mv. But what about the velocity? We don't have the velocity, plus we don't have an additional information given in the question. But remember student, this is a photon. So photon is a constituent of light. Okay. So basically, photon will have a zero mass when it is moving with some velocity. So this is very important to note. If a photon is moving with a very high velocity, in that case, it becomes massless. Okay, not in every case. If it is still, it will have a mass. Got it? How you will calculate this? What will be the velocity of photon? If it is light, any guesses? What will be its velocity? So it's very simple. So it will be 3 into 10 to the power 8 meter per second. Yes, you can take it 2.9 into 10 to the power minus 8 plus 8 also. So what will be the unit? Meter per second. Now first we will convert this lambda into meter because our light is in meter per second. So you will convert the wavelength also into SI unit. So to convert angstrom into meter, you will take 10 to the power minus 10 as a factor. Now, as I have told you, velocity of photon will be equals to the velocity of light. So we were interested in the mass. So mass will be equals to h by lambda v. Just put all the values again. H value will be same. Lambda is given. V we know. So we will get your answer as 6.135 into 10 to the power minus 29 kg. So this is a very small mass. Now due to this very small mass, its wavelength is significant, but still it is very small, 3.6 into 10 to the power minus 10 meter. But remember student, our photon is also very small. Okay. So due to this small size, its wavelength is very significant. Okay. So if you see a photon in real, so if you take a hypothetical case and if you're seeing a photon, you will see it moving like this. Okay. Now we will see the Heisenberg uncertainty principle and its aspects. So this is the formula. Delta x into delta v should be greater than or equals to h by 4 pi m. Okay. So this is the equation. Now we will try to understand the aspects of this equation. Let's see. So first of all, what is delta x and delta v? So they are the uncertainty in the measurement of position and velocity. Okay. Now the point here is that if suppose the delta x is small, then what will happen? The velocity will be very high. This will be true. Okay. Now, what is the second case? So, the second case would be that if this is low, then this will be high. So, the point is that you have to keep this product as h by 4 pi m, or it should be greater than h by 4 pi m. Okay. So, if we carry out physical measurement, it is very obvious that you won't be able to calculate the electron's position as well as the electron velocity at the same time. If you do it, then the picture will be blur or fuzzy. So, why are we saying this? Why are we not able to calculate its its velocity and position at the same time? So the reason is that, suppose you are trying to look at something. You are looking at a table. How are we able to look at it? The reason behind it is that the visible light that is present around you, it is striking the table. Some of the part is absorbed by the table. Rest of it is going to your retina and you are able to see that table. Okay, very good. But what about an electron? Its size is very small and the wavelength of the visible light is very large. So suppose your electron is a dot and a light is coming. So if its wavelength is very big, suppose this is your dot, a very small, and there is a chance that your light will skip the electron, and it happens most of the time. And due to that, you are not able to see the electron. Okay, because adequate amount of light is not reflected back to your eyes. But what about the electromagnetic radiation, which are smaller in size, whose wavelength is very small? In that case, it is possible. So suppose a smaller wavelength light is going. So there is a larger chance that it will strike the electron and that will be reflected back to your eyes and you will be able to see that electron. But the problem is that our eyes cannot detect that smaller wavelength. It can only detect in the visible region. Okay. So what we can do? So we have used some sophisticated method to detect that light which is not recognizable by our eyes with the help of some sophisticated machines. Okay, so suppose we take a wavelength that is small enough to detect the electron. So it will go and attack the electron, or it will radiate on the electron. Then some part of it will be absorbed and some of it will be reflected back to the eyes. So it is possible that one of the visible region may be striking, but there should be enough amount of light that should be reflected back and go to your eyes, or else you would not be able to see it. Okay, so one photon, I guess, is not enough. Its intensity will be very slow and that is not visible. Now suppose what we do, we are taking a sophisticated machine, we are radiating it with a light that is having a very low wavelength. But if the wavelength is low, then the frequency will be high. Okay, and if the frequency is high, energy will be high, because C is equals to nu lambda. So nu is inversely proportional to lambda and E is equals to h nu. So energy and frequency are directly proportional, whereas wavelength and frequency are inversely proportional. So you decrease the wavelength, you increase the frequency, and you increase the energy. So you are giving a higher energy to the small particle. What will happen as a result? So what will happen? The light will go, strike the electron, come to your eyes, you will be able to see the electron. But the difficulty is that its velocity is changed. Why? Because we have applied a large amount of energy to a very, very small particle because of that high frequency electromagnetic radiation. because electromagnetic radiation is a form of energy. Therefore, its velocity is changed. So now you are able to see the electron, its position you are able to identify, but its velocity is not clearly determined. It is a distorted one. You have changed that velocity. Now, second case, what we can take, you can apply a bigger wavelength. Now, in that case, you won't be getting the idea of the position very clearly. So the overall thing is that if you try to determine the position, you will have difficulty in determining the velocity, and the vice versa is also true. I guess this thing is very clear to you, and it's something that is behind this equation. Okay, the practical thing. So if you are not able to understand this equation, you can get the physical meaning from my explanation. Now, what is the significance of this uncertainty principle? First is that if you are aware about the position and velocity at the same time, you won't be able to detect the trajectory of the electron or the path of the electron. So this is very, very important. How do we understand it? Suppose we are taking a system, we are taking a ball. Now in its initial position is 0, and we are taking it at time t is equals to 0, and its initial velocity is 2 meters per second. So these are the initials of the given ball. Now, if it is so, can we calculate the position at a later time? Suppose we are using the equation of motion and calculating it. So in this equation, it is very simple. You know the formula for velocity. It is initial position by final position minus initial position by time. Just rearrange it to get this equation. Now you know all the values. Just try to calculate this. Initial is x, okay? So x, we are interested in considering it. So x is the final one, not the initial one. X naught is the initial one. So if we do the calculation, you will get after t is equals to 5 seconds, the position as 10 meter. Now you know that after 5 seconds, your ball, which was at a 0 meter distance, suppose you are taking a coordinate, after 5 seconds, it will move 10 meters. But how we are able to calculate this? This is important. So for that, you must know the initial position and the initial velocity. Then and then only you will be able to calculate its position after some time, or you will be able to know its trajectory. Now, what is uncertainty principle? We cannot know these two things with precision, and that is the reason we cannot get the correct trajectory of the given microscopic particle. Okay, so this is the very meaning of this. I guess it is clear to all of you. So this is just an illustration to understand the idea behind this. Now moving on further. What is the second significance? So we have seen this. It is only for the microscopic object. Again, this uncertainty principle is also for the microscopic object. It is good for macroscopic also, but again, it is not significant. Let us try to understand it, why it is so. Suppose we have a mass of about 10 to the power minus 6 kg. That is about a milligram, a small amount we are taking. So what will be the product of the uncertainty in velocity multiplied by the uncertainty in position? So that will be h by 4 pi m. Okay. So h value is 6.626 into 10 to the power minus 34. Pi is we know, m is given. So you will get a value of 10 to the power minus 28 meter square per second. Now see student, the product of the uncertainty is very, very small for this even a milligram amount. Now consider a larger object like 6 kgs or 7 kgs. In that case, this value will go even down because we are increasing this mass. Are you getting the point what I am trying to make here? So this is very important. These 2 points are very important. So you know, read it in the textbooks and all, that you won't be able to predict the trajectory. If you know this path, that how we are not able to know the trajectory. So you will get your answer directly from the equation of motion. I have told you earlier. And second thing is this. Now moving on further. Now we will talk about the significance of uncertainty principle, third point. So third point, we know it very well. The precise statements of position and momentum of electron have to be replaced by the statement of probability. Okay. So initially we were saying that in the Bohr model that there is a definite path for the electron to move. We have seen it. But now we are replacing that definite part with the probability term, that we can predict that the electron may be here. But we can't say that it will be here with 100% accuracy. It's not possible now because we don't know its position and momentum. Then how we will interpret its position and velocity? It's impossible now. So therefore, the idea of the definite position is given up. And now we are moving to the probabilistic theory or the probabilistic model, which is called as the quantum mechanical model of atom. So these 2 principles are very important to understand the quantum mechanical model. Now at the end of the class, I will try to re-explain the Bohr's model for those who have not understood in the previous class, because we were lagging time. So I will try to make you understand that also. Okay. Now what is the reason of the failure of the Bohr model? We know it that the Bohr model was not able to explain some of the drawbacks. Now what was the reason behind its failure? So that is to be understood right now. So the first difficulty with the Bohr model was that it was defining the circular orbit. A well-defined circular orbit was according to the Bohr's postulate. Second thing, he didn't took the wave nature of the electron. He only took the particle nature of the electron. Okay. But according to de Broglie, every particle, where macroscopic or microscopic, has a wave nature as well as a particle nature. But due to this rejection of this wave nature by the Bohr, he wasn't able to explain the things more detailed. Third thing is, since Bohr was giving well-defined circular orbit, but on the contrary, Heisenberg uncertainty principle was saying that no, it is not possible to give the trajectory or give the defined path because we don't know its exact position and exact velocity. So you can see that how these 2 models are defying the postulates of the Bohr model. Now next, since Bohr model ignores this dual behavior of matter and also contradicts the Heisenberg uncertainty principle, we have to leave this atomic theory behind and move with a new mechanics known as quantum mechanics, which is going well with this Heisenberg uncertainty principle and wave particle duality. So it is consistent with both of them. Okay. So this was all about the de Broglie and the Heisenberg uncertainty principle. Now we will try to understand the Bohr model once again. Okay. So students, so you have to listen it very carefully. Okay. So each point is very, very important for the Bohr's model for hydrogen atom. So first point is that the electron in a hydrogen atom can move around the nucleus only in a fixed radius and energy, and Bohr named them as orbits, stationary states, or allowed energy states. Okay, so this was his first postulate. Easy to understand, not a difficult one. He just gave a name and he said that it will only revolve in a fixed orbit. Rutherford said that it can revolve in, it is just revolving around the proton. No fixed word was used there. Second was that if the electron is moving away from the nucleus, then it will be in a higher stationary state. And for that, it will require energy. Okay. So suppose this is your electron. This is your first state. This is your second state. So if an electron has to move from this state to this state, then it will require energy to do so. Okay. Because this energy, this state is a higher energy state. And this thing is discrete in nature. So if there is a state which is having an energy of 1 joule, okay, then it may be possible that in between these two states, there may be various energies that are possible. But since the energy is discrete, it will have only a certain amount of energy after that. So it can be anything depending upon the electron and proton. Now, why it is so? Why is this discrete? We have seen this thing in the quantization of energy. Any doubt in this two part? So it's very simple to understand, I guess, that electrons are present in a stationary state, and to go from a lower stationary state to a higher stationary state, it will require energy to do so. But it cannot go in between. It cannot go in the region between these two regions. Okay, between these two cells. Okay, can I move forward? Now, what was the third postulate? So suppose during the transition, it will emit or absorb energy. Okay. Now, what will be the say frequency of that light that is emit or absorb? So it is given by nu is equals to delta E by H. Okay. So suppose during transition, if it is going from a lower energy state to a higher energy state, it will absorb energy. Or if it is going from a higher energy state to a lower energy state, it will emit energy in the form of electromagnetic radiation. And what will be its frequency? It will be delta E by H. We know that E is equals to H nu is the formula for the energy of the radiation. So from there it is coming. Now we have written it as delta E. Why we have written it as delta E? Because this is the same energy which is required for the transition. Suppose it is 1, this is 2. Now when you have to go from here to here, you will require a definite amount of energy, which is the energy difference between these two states. So we have written it as delta E, that is E2 minus E1. So you can take any initial and final state. So this is the final state where the electron is going. This is the initial state. Is it clear to you? So if you know the energy of the two states, you can know that what frequency of light it will emit or absorb while going from one part to another. Any doubt in this part? So here it is given E1 and E2 are the energies of the lower and the higher allowed energy state. Now remember student, it can only go to a definite energy state. So this is important to note. This rule is also called as the Bohr's frequency rule. Now, what is the fourth point? Fourth point is that we are saying that okay, the electron can revolve around only in a definite orbit or in a different state. But how do we know that which state is that or which energy should be that? For that, he gave the quantization of angular momentum. Okay, he gave the quantization of angular momentum. It is given by mvr equals to nh by 2 pi. So he was saying that suppose an electron is moving in an orbit, so it will revolve only in that orbit where its angular momentum, which is mvr, is equals to nh by 2 pi. Now n can be any integer. So it cannot be possible that its angular momentum is equals to half h by 2 pi. It's not possible. This n can only be a integer 1, 2, 3, right? Is this part clear to you? So this is very important to understand. Okay, yeah, n will be discrete. It will always be a whole number. It can't be a fraction. So as I have said, if I am telling it for the electron, then me is the mass of the electron, v is the velocity, and r is the radius of the orbit. So these 2 points are very, very important, and these formulas are also very, very, very. So basically, say 2 types of momentum are there. One is linear momentum and one is angular momentum. If an object is moving, then if it is moving in a circular motion, then it will have 2 type of momentum. Linear momentum will be there, which will be simply m into v, mass into velocity. But if we have angular momentum, then it will be mv cross r. So suppose your electron is moving like this. If this electron gets detached from the proton, then in which direction it will move? It will move like this. You know it very well. Just take a ball, attach it to a string and rotate it, and cut the string at any instant. The ball will move tangentially. Okay, so that same, now there is a momentum for that to go in that direction. So that is called as the angular momentum, which is given by mv cross r. Okay, no, it is not a force. It is momentum. Momentum and force are 2 different things. Is it clear to you? So quantized meaning means it can take only certain values. Suppose you are on a stair, you are climbing a stair. Okay, so you can be on a stair, but suppose there are 2 stairs like this. Okay, so one is this and one is this. So either a person can be here or it can be here. So I'm talking about the ideal condition. So it can't be in between. Okay, so that is called as quantized. It can take only certain values. Got it? So this is the simple meaning of quantized. If you are still having an issue, you can go and watch the previous lecture. There is a illustration of that. Now, what are the results of this Bohr's theory for hydrogen atom? So he took this postulates, and as a result, he got some equations. Okay, so what are those equations? So first is, we know that electron can be in a stationary or a well-defined object, well-defined circular path. So that stationary state is denoted by n is equals to 1, 2, 3. So the first one will be the n is equals to 1, then the next one will be 2, then the other will be 3, and so on. Now remember students, that mvr is equals to written as nh by 2 pi. Okay, so there also that n value that we were talking about, it was this one. Okay, so this should be remembered. This is very important. So its angular momentum must be a integral multiple of its stationary state's number. Now, using those postulates and using some calculation, he derived the radii of the stationary states, of every stationary state. For n1, he has a different radii. For n2, he has a different radii. N is equals to 3, he has a different radii. In general, we can write it as Rn is equals to n square a naught, where n is this one. Okay, so if you are considering the radius of the first orbit, just put n as 1 and use it to calculate the radius of that orbit. So suppose you want to calculate the radius of the first orbit. So for the first orbit, n will be equals to 1. If you put the value of n as 1, and a naught value is fixed, so it will be always taken as 52.9 picometer. Remember this value. Put this 52.9 here, take n is equals to 1, then what will be the radius of the first orbit? It will be 52.9 picometer. Okay, then if I ask you what will be the radius of the second orbit, just take n as 2, then 2 square, that is 4 multiplied by a naught value is again 52.9, you will get your radius of the second orbit, and so on. I guess it is clear to all of you. Okay, now let us move to the next result. So the next result is very, very important. It is related to the energy of that orbit. We know the radii of the orbit, we know the stationary state's number, that for one it is first state it is 1, second it is 2, and so on. Now what about the energy? Again, a simple formula. So energy of nth state in which we are interested in, it can be 1, 2, 3 or any one. You can simply use this formula minus RH by multiplied by 1 by n square. Again, RH here is a constant similar to the A naught, but it has a different value, of course. So that value is 2.18 into 10 to the power minus 18. So this is the value of the RH. So remember, student, this is the same Rydberg constant that you have seen earlier. Okay. If you don't remember, no problem. Just go back and see. So for now, you can consider that RH is a value that has been calculated by the Bohr. Now, value of the first orbit's energy will be, just take n is equals to 1. So 2.18 into 10 to the power minus 18 multiplied 1 by 1 square. You will get the energy of the first orbit. Then what will be the energy of the second orbit? Just take n is equals to 2. So there will be 2 square here and you will get the energy of the second orbit. Any doubt till now? So we have gone through 3 results. So this is the third one. Now we will move to the derivation part. So this is something which is very much related to the physics, but since it is given in your JEE and NEET syllabus, so I am considering that derivation. Okay. So just listen to each and everything. Some things, some parts of the derivation may be assumption. Okay. So you have to assume it if you don't know the value of that exact thing. Okay. So let us move to that derivation. Before that, we should understand that why is the energy coming as negative? Why are we considering? If you see, go and see back, it was minus 2.18 into 10 to the power minus 80. So why it is negative? That thing is important. So if I convert that minus 2.18 into 10 to the power minus 18 into electron volt, so just multiply 2.18 into 10 to the power minus 18 with 1.6 into 10 to the power minus 19. So this is the conversion of joule to electron volt. You will get it as 13.6. Yes, it is calculated for electron. Similarly, for second, you will get 3.4. For third, you will get this. What about infinite? So you can see that energy was directly proportional to 1 by n square. So if n is infinite, that means 1 by infinity square. So E will be equals to 0. Okay. So therefore, at infinite distance, the electron's energy will be 0. Now, here the negative sign is indicating that the energy of the free electron is higher than the electron that is bonded to the nucleus. And as it is getting away from the nucleus, the energy is becoming less negative. So the value of infinite square will be infinite square. So as we are moving away from the nucleus, the value is becoming less negative in case of energy. It is showing that your electron is becoming less stable, because more negative energy means less energy. If less energy, then more stable. Okay. And if less negative energy, then more energy, which is less stable. Is this point clear to you? So this value is smaller than this value, means the electron in the first ground state will have a lower energy as compared to the second ground state. Because of this, it will be of higher stability. So on, if you go on to the infinite, so it will have the maximum energy, which is 0. So it will be the least stable one. So the value of infinity square will be infinity. Now moving on forward. So as we move closer to the nucleus, we can see it that as we are moving from infinity to the nucleus, the energy is decreasing and the electron is becoming more and more stable. Now, one more important thing. This equations that we have seen right now as a result of the Bohr's model, so they are only applicable for hydrogen and hydrogen-like species. What are hydrogen-like species? That have only one electron. Like your helium, it has one electron, helium plus. Okay, not helium, helium plus. Lithium 2 plus. Also it has 1 electron because the neutral lithium has 3 electron. If you remove 2, you will get again 1 electron. So those equations were only applicable to hydrogen and hydrogen-like species, which are helium plus, lithium 2 plus, and beryllium 3 plus. So all of those which have 1 electron are hydrogen-like species. But there is a small change in the equation. If you are calculating the energy, you have to keep the whole equation as same, but you have to multiply it with a Z square. Now Z is what? Z is the atomic number. For helium it will be 2, for lithium it will be 3. Okay, yeah, all of those which are isoelectronic with the hydrogen, those can be used according to this equation. How do we calculate the radii? So just take the original formula, which is 52.9 n square or a naught n square, and divide this thing by Z. Again, Z is the atomic number. Now, how do we derive it? So let us first consider the Bohr's postulate for hydrogen atom. Just follow this the way I am telling. You will get the derivation. First is, we know that electrons are revolving around the nucleus, and the only reason they are attached to the nucleus is the electrostatic force of attraction. A positive and negative charge attracts each other. Second thing, the angular momentum that was written previously and the allowed angular momentum was given as MBR equals to 2nh by 2 pi. So you have seen this equation in the previous part. The only allowed angular momentum is MBR by nh by 2 pi. Okay, any doubt in this equation? You have seen this equation. Okay, so these are the two postulates that we will use. Now next, to make the electron revolve, the centripetal force should be equal to the electrostatic force. Now what is the meaning of this? Suppose this is your electron that is revolving around the proton. Okay, so since they are oppositely charged, they will attract each other, and that force is denoted by the red arrow. But if something is revolving in a circular path, it is always facing a force outward. Okay, outward force. So if you are, suppose you are on a ferry, okay, you must have seen the ferries in the melas, and there you have seen that if it is revolving, then you will feel an outward force. Now that force is called as the centripetal force. Okay, so these two forces, the centripetal force and the electrostatic force, if these two are equal, then and then only your electron will be in this orbit, or else it will be distorted or it will be thrown out. Now what are the values of these two forces? The electrostatic force will be Zke square by r square. So this is just used formula for the electrostatic force of attraction. You can go back to the physics and look for this formula. It's very easy to understand. Why we have taken Z? Because if we have multiple number of protons, we have to take the charge on the nucleus as Ze, and for one electron the charge is E. So two things are there. For multiple protons the charge is Ze, and for the electron the charge is E. So Ze multiplied by E, that is Ze square. That is equals to the centripetal force. Now here, K is the Coulomb's constant, E is the charge of electron, and Z is the atomic number. Because whatever be the atomic number, that will be the number of proton present in the nucleus. Okay. Now next, what we can do? What will be the expression for the radius? So for the expression of the radius, we will use the before two equations. So first one was this, MBR is equals to nh by 2 pi. You take the velocity from here and substitute this value of V in the force equation that we have seen, that centripetal force is equals to the electrostatic force of attraction. If you do that, you will get this equation. Okay, Zke square by r square is equals to MVR. So instead of V, we have taken this value from the quantization of angular momentum. From here, you will get the value of the radius. Okay. Now, what about the value of energy? Let us see for that. So to calculate the expression of energy, we know that the kinetic energy is equals to half mv square. So many of you have answered also the same answer. What will be the potential energy? Obviously, that will be minus zke square. Again, potential energy will be the electrostatic potential. Okay, Z will be considered here. So here it will be Z. We know that this zke square is equals r by r square is equals to mv square from the previous equation. Therefore, mv square is equals to zk square by r. Just put the value of mv square here. What we will get? Half zk square by r square. So this is the new kinetic energy if we take the equation of force and take the value of mv square from there. So this is just a derivation. Take it simply and you will understand that thing. Therefore, what is the total energy? Kinetic energy plus the potential energy. So that will be calculated as minus half zk square by r. So we know the value of radius from the previous equation. Just put it here and you will get the equation for energy. Now you have got two equations, one for energy and one for radius. But many parts of these two equations are constant, like this one, mass, k. Now if you put all the values of this, then you will get the equation that you got in the Bohr's postulate. So this is a homework for you. You already know the value of k. We have seen it in the previous part. Just put all these values and you will get the equation for the radius and the energy that we were seeing in the Bohr's postulate. So this was all for today's class. Thank you.